Okay, so a couple of announcements. First, I postponed the homework until Monday. Secondly, these are the, well, before I say that, before I say anything, a homework was turned in, but without a name.
Yeah, that was my extra.
All right. So here's what I want you to do. I want you to take this to Charles Shirkwe and tell him to give, to attach whatever points to it. In other words, to adjust your grade appropriately.
Yeah, because I was supposed to attach this.
Okay. All right. Next, when Charles did the grading, he forgot how many problems there were and just deducted points from 10 times the number he thought was the correct number of problems. It turned out that was not the right number of problems. So everybody's grade for either this homework set or the previous one, I don't remember which he said. I think it's this homework set. Everybody's grade goes up by 10 points. But he didn't bother to change the grades on the papers, so you should add 10 to this. That can't be right. That means this guy then has.
I think that's the first homework, because the first homework he did it at a 90, but he only took like 4 points off my homework, and I got a 76.
It might be the, oh, then that may, yes.
So that would
It may have been the first one. On the other hand, all right, look, I don't know. You have to ask him about these things. So he put the homeworks in your boxes, but some people don't have boxes. So there's somebody named Demosthenes Cantana, Chechen Mao, Bob Keating, Akash Rakolia, Vlado. Boy, this is pretty much. I would suggest that you staple your homework and also print your name.
Okay, about that.
Casey Rhodes. All right. Daniel Zierzow. Is that right? Zierzow?
Yeah.
Swerum Jung. Paul Klimov.
President.
You got that? Oh, I'm sorry. Oh, shit. I thought I had finally got your name. Ben Oliker. Garrett McMath. Huge name, McMath. Especially for me. Chris Virgin. Clint Zeringer. Sherminha Rastani. All right. Okay, what am I seeing here? All right, so that's the administrative stuff. What I'd like to do now is redo the transition from the Fourier series to the Fourier integral. I did that last time, but I figured out how to do it more clearly. So let me try to do it more clearly. All of those just so appalling. All right. Well, let's look at the Fourier series relation. N to minus infinity plus infinity, C sub n, e to the I, pi n x over L, divided by the square root of 2L. This is I'm doing an interval. The interval in question is from minus L to L. Minus L to L. And C sub n then is an interval from minus L to L of e to the minus I pi n x over L f of x dx over the square root of 2L. Okay, so those are our Fourier series relations. Now the question is, what happens as you let L go to infinity? And what I want to do is I want to use something called the nearest integer function. So this is the nearest integer to the real number and so in other words, y is equal to say n if the absolute value of y minus n is less than a half. So that's the nearest integer function. Turns out there's a subtlety in the nearest integer function because you always have, well, what do you do with it? Suppose y is equal to 2.5. The convention is the nearest integer is 2. The nearest integer is an even integer if you're on that breakpoint of a half. So the nearest integer for 0.5 is 0. The nearest integer for 1.5 is 2. Okay, so what I'm going to do then is promote Cn to a function of a real variable, C of y, and C of y is C sub nearest integer of y. Okay. So consequently, C of y will be C sub n if y minus n is less than a half. Okay? Now, with that definition, we can transform this into an integral. So I get f of x is equal to sum minus infinity, well, n equals. N equals infinity to minus infinity from the integral from n minus a half to n plus a half of C of y e to the I pi y x over L over the square root of 2L dy. And literally, actually, now that I think about it, we should actually, to have this to be an equality, we should have this be the nearest integer to y times x over L. Okay, so in other words, this is really an n. This is effectively C sub n. And we're doing an infinite set of integrals. Each integral is just though the integral dy. The integral dy here is just equal to C sub n e to the I pi n x over L divided by square root of 2L. So it's exactly the same thing as this. All right? But in the limit, as L goes to infinity, the difference in phase between the nearest integer of y, or the nearest integer to y, and y is extremely small because that difference is divided by capital L, which is going to infinity. So in other words, this thing, okay, so let me next go to the point where this is really an integral from minus infinity. In other words, we can rewrite this as an integral c of y e to the I pi nearest integer to y x over L dy over the square root of 2L. And now we make the transition as L goes to infinity. Well, it hasn't yet gone to infinity because I've still got it there. C of y e to the I pi yx over L dy over the square root of 2L. So those are the, in other words, to do this transition rigorously, this is what is involved. The treatment I gave you last time on Monday is what I had seen in most textbooks, where they just basically go from the Fourier series to this by setting dn equals 1, which may not really doesn't mean anything.
To go from that one step to the next, you're just assuming that L is infinite?
L is going to infinity.
Going to infinity.
Yeah. So in the limit, in other words, the phase mismatch when you do the integral is at most e to the I pi x over 2L, because the difference between y and n, y and nearest integer to y isn't any bigger than a half. And this phase factor goes to 0 then. I mean, I'm still not doing it rigorously, but for this side of Columbus, it's rigorous. All right. So now what we want to do is change variables. We're going to change variables to k equal to pi y over L. In that case, f of x is equal to the square root of L over 2, an integral minus infinity plus infinity, c of Lk over pi e to the I kx dk over pi. So in other words, dy here, this is the dy. dy is equal to L over pi dk. And so then you have the L over pi, that gives you the square root of 2 just sits there, and the 1 over pi comes over here. All right, the next step, questions? The next step is to define f hat of k as the square root of L over pi times c of Lk over pi. And when we do that, what we have then is c of Lk over pi is equal to the square root of pi over L times f hat of k. And so then substituting in here, the square roots of L cancel. 1 square root of pi turns this into the square root of pi, and the square root of 2 just comes along. And so this is an integral minus infinity plus infinity f hat of k e to the I kx dk over the square root. All right, so that's a quasi-rigorous, or at least it satisfies me. I don't know how you feel. It's a lot better than just saying dn equals 1. Okay, now we want to get the expression for f hat of k, and for that we just use the definition of f hat and the definition of c of y and our formula for Cn, which is the Fourier series formula. And so what we find then is f hat of k is the square root of L over pi times c of the nearest integer to Lk over pi, which is the square root of L over pi integral from minus L to L e to the minus I pi n x over L and the square root of 2L into x dx, which is then the square root of L's cancel. We have 1 over square root of 2 pi, so this is equal to minus I to L f of x e to the minus I kx dx over the square root. Now we take the limit, L goes to infinity, and we get f hat of k is the integral from minus infinity to plus infinity, f of x e to the minus I kx dx over square root of 2 pi. The other relation is this one, which says f of x is equal to the integral from minus infinity to plus infinity of f hat of k e to the I kx dk over the square root of 2. Okay, so these are the famous Fourier relations for the Fourier transform and the inverse Fourier transform. Technically, if you start with the function f of x, then f hat of k is the Fourier transform. So this is the Fourier transform. This one that gives f of x in terms of its Fourier transform is called the inverse Fourier transform. However, there's no convention really on whether you have a minus I or here and a plus I here. It's just that if you have a minus I here, you've got to have a plus I here. And if you decide you want a plus I here, you've got to have a minus I here. Similarly, the product of the two things that divide dx and dk have to be 2 pi. And you can put the 2 pi here or the 2 pi there, or do it symmetrically the way I have. At least with the Fourier transform, though, the integral is minus infinity to plus infinity. So you don't have any ambiguity about the integral. Okay, so that's the Fourier transform. Questions? It's used, of course, a lot in electromagnetic theory and field theory, quantum mechanics, quantum field theory. All right, we were doing an example last time of Gaussian f of x equal to e to the minus m squared x squared. We have then f hat of k. Its Fourier transform is dx over root 2 pi e to the minus I kx minus m squared x squared. And then what we do is we write that as a square, so minus infinity to plus infinity dx over square root of 2 pi e to the minus m squared times x, something or other squared, and then a compensating factor. And then in order to get this minus ik, we need a plus ik, and then the numbers have to work out. So it has to be something over m squared, get rid of the m squared, and a 2, because you get a 2 from the formula for squaring a plus b. On the other hand, this thing squared is minus k squared over 4, m to the 4th, and so that's times this is plus k squared over 4m over 4m squared. And so you need to multiply by e to the minus k squared over 4m squared. So that's the completing the square argument there. And now, as I said to you, the integral, if you imagine this to be kind of an integral in the complex plane, the integral along the x-axis of this function is the same thing as the integral lower down at lower x by ik over 2m squared. And so this is something we'll learn when we do complex variable theory. So this is equal to the e minus k squared over 4m squared, which is the main part. You know that whatever this thing is, it's a number. Well, it has a k dependence, but the k dependence is an illusion. K is not involved. So this is dx over the square root of 2 pi e to the minus m squared x squared. And once you do that, then this is, so the answer is that this is equal to, let me erase this. So the answer is that f hat of k is 1 over m root 2 e to the minus k squared over 4m squared. That's one of the nice things about Gaussians, namely that you can do the integral by completing the square. Once you complete the square, most of the answer is just a term that compensates for completing the square. And the thing that's left over is normally just a number. And in fact, when one does path integrals, the path integrals that one really does are Gaussian path integrals. And then you've got this, after you complete the square, you bring the thing out, and the other thing that you've got there is some horrendous path integral. But you agree only to compute ratios of path integrals. So you just say, well, it's a number, I don't care what it is, and it cancels when you do ratios. So that's how that works. If you're curious, by the way, the path, you should be able to read the path integral chapter if you're interested. Chapter 12. Okay, so where are we? Well, now the question is, did he screw up? And one way to check that is to express f(x) in terms of its Fourier transform f hat of k by the inverse Fourier transform, which is to say that f of x is equal to an integral minus infinity to plus infinity pk over the square root of 2 pi at hat of k e to the I kx. So this is integral minus infinity plus infinity dk over the square root of 2 pi 1 over m square root of 2 e to the I kx minus k squared over 4m squared. And so once again we complete the square in the exponent. And so we write this as minus infinity plus infinity dk over, I guess it's 2m square root of pi e to the, and so we want minus 1 over 4m squared times k, and then some extra thing here that will produce this, and so it's got to have an x. It's got to have a minus ix. It's got to have an m squared. And let me get this straight. Now if we do it, we get a, okay, it's got to have a 2 here. Is that right? Yes. Okay, so that's it. And then when this thing happens, that is to say, when you multiply this out, you get an extra term. The extra term is minus 4x squared m to the 4th. The 4 m squared divides into that and just gives you e to the minus m squared x squared. Once again, the integral of k in the k plane, you can say it's the integral along the k-axis, well, is the same as the integral on a horizontal integral, but 2ix m squared higher, and so this thing is just e to the minus m squared x squared times the integral from minus infinity to plus infinity dk over 2m root pi e to the minus k squared over 4m squared. And then that Gaussian integral you can either do or look up, and finally what you get is that this is equal to just e to the minus m squared x squared, which is reassuring because that's the f of x that we started with. Okay? And the important thing, one important thing here is that if you have a Gaussian and m is small, then this Gaussian is very spread out. You have to go out to large values of x in order for this thing to be small. If m is small. In that case, though, m is small, and then when you go out from 0 by just a tiny amount in k, you're already very suppressed. So what you have is that if this is f of x, then f of k looks like this, and on the other hand, if f of x looks like this, then f hat of k looks like that. So there's an inverse relationship. And this, as we'll see in a little while, I think we'll get to it today, one application of this in quantum mechanics is to the relationship between the wave function in position space and the wave function in momentum space. And what you see is that if it's peaked in position space, then it's very flat in momentum space, and it's flat, and if it's peaked in momentum space, it's very flat in position space. And that basically is interpreted as saying that you can't have a state that has both the position of the particle and the momentum of the particle well defined, or really small, or just arbitrarily small. But as you try to squeeze one, the other one must expand. Okay, so is there a question or two? Questions? Glad to see nobody's coughing today. We had a colloquium speaker a couple of weeks ago, and he drove off Saturday morning after the colloquium, and I sent him an email message, maybe two. I didn't hear a word from him. I thought to myself, well, I didn't give him a very elaborate introduction. Maybe I hurt his feelings or offended him in some way. I got an email from him saying, sorry, I didn't write sooner. But as soon as I got to California, I came down with a bad case of the flu. So it's out there. I called local. I plan to get a flu shot tomorrow, but it's just a flu shot for the ordinary flu, not for a big flu. I think you guys can get 3 flu shots from the Student Health Services somewhere. And you should. But you get 2 shots, one for seasonal flu and one for big flu. Okay. So these are the Fourier relations, Fourier transform relations. What if the function is real? So suppose f of x complex conjugate equals f of x. If, then what? Well, f hat of k is the integral minus infinity plus infinity f of x e to the minus I kx dx over the square root of 2pi. Okay. That means then that f hat of k complex conjugate is equal to the integral minus infinity plus infinity. Well, when we do the f star, nothing happens to f because it's real, but the f star here gives us e to the I kx dx over square root of 2pi. But this is just f of k, f hat of minus k. Because f hat of minus k is this formula. So the relationship then is that f star of k is f of minus k, which is similar to the rule we had for Fourier series. Okay?
So are those f hats or f's?
Oh, duh. Thank you.
Check out 318.
Say it again.
So I think that equation 318 should have.
God, you're right. Thanks. So, I normally cite students in the preface. Why don't you print your name? And also I cite students in typos. You showed me a typo, but I didn't get your name.
Okay, I'll get you my name.
Thank you. Why don't you just sort of write it on, let me see what I'm doing now. Okay, so the next thing is to go through the razzmatazz. Yeah, well, it's good to get it back. I made far fewer mistakes when I'm reading the notes. Okay, so remember that we found an expression for the delta function for a Fourier series. In fact, we found various expressions depending on the interval and whether the function is complex or real. In any event, let's just look at the general Fourier, actually inverse Fourier transform notion of hat of k e to the I kx. This is then integral minus infinity plus infinity k of the square root of 2pi e to the I kx. And now we use the formula for f hat to get minus infinity plus infinity, and I'm going to use the variable y instead of x. Y square root of 2pi e to the minus I ky of y. So we could rewrite that as integral minus infinity plus infinity plus infinity dk over 2 pi edik x minus y f of y and y. And remember, this is f of x. So once we've done that, what we see is that we have an expression of the direct delta function, because this is what we'd expect from the direct delta function, delta x minus y, f of y, dy gives us f of x. So that tells us then that this Fourier relation is a representation for the direct delta function that's appropriate for the sort of functions that have nice, smooth Fourier transforms. And so we say delta x minus y then is integral minus infinity dI x minus y dk over 2 pi. And you can have a minus sign. Obviously, the delta function is real, so if you complex conjugate it, you get a minus sign here. In other words, you can use plus I or minus I, depending on which is more convenient. So that's an expression for the delta function, and we might compare it with a previous expression, 1 over L, sum n equals minus infinity, plus infinity, e to the I, 2 pi n x minus y over L. So here we have two different expressions for the delta function. And the point is that this expression is for functions that are smooth and periodic with period L. And these are for functions that are smooth and square integrable. That is to say, integral f of x squared dx minus infinity plus infinity is finite. Bring it very close to it. Okay, so that's the difference between them. They're different representations for different delta functions. Remember, a delta function is a function. It's a map that takes functions and maps functions into numbers. It's what's called a generalized function or distribution. If you ever need to have details of distributions, there's a set of Russian books by a mathematician named Gelfand, if I remember correctly, that deal with generalized functions. And the remarkable thing about these books is that, although they're written by a mathematician, they're intended to actually be readable, which distinguishes them from almost all math books written in the last 100 years by either American, British, or French mathematicians. I don't know where the Italians are. I suppose it's the socialism of the Soviet Union that indicated to the mathematicians that they were supposed to communicate with ordinary people in ordinary Russian. But actually, I'm not a sociologist, so okay. Now, why is the square integrability involved? Well, we can define an inner product of functions f and g, and the natural inner product of such functions is an integral f star of x, g of x, dx. That's a natural inner product. And so let's rewrite this in terms of Fourier transforms. Well, it's integral minus infinity plus infinity dx then. Now f star then is going to be integral minus infinity plus infinity dk over the square root of 2 pi f hat of k e I kx, all Latin complex conjugated, and then integral minus infinity plus infinity dk prime over the square root of 2 pi g hat of k prime e to the I k prime x. And, well, just to save some time and writing, notice that what we've got here is an integral. Well, maybe I better do it in more detail. So we have an integral here. We can say it's from minus infinity plus infinity dk, integral minus infinity plus infinity dk prime, and now the integral from minus infinity plus infinity dx over 2 pi e to the I x k prime minus k. Now let me put parentheses around that. F hat of k star g hat of k prime. So that's what that expression is rewritten. But you notice that this thing is the delta function of k minus k prime. So, what we have then is that fg is equal to integral minus infinity plus infinity dk, integral minus infinity plus infinity dk prime, delta k minus k prime, f hat star of k e hat of k prime. Well, the delta function makes that vastly simpler. It's just integral minus infinity plus infinity dk f hat star of k g hat of k. So in other words, this inner product looks the same whether you write it in x space or in k space. And this, in fact, is called Parseval's relations. So this is Parseval for Fourier transforms, and last week or so we did the Parseval relation for Fourier series. In particular, if you set G equal to F, and you have the inner product of F with itself is the integral minus infinity plus infinity f of x squared dx, which is the integral minus infinity plus infinity f hat of k squared dk. So that means that if a function is square integrable, then its inner product or its norm squared with this definition of inner product is finite, and it's equal to the inner product of, in other words, you can say this is the inner product of f hat with f hat, and they're equal to each other. So this is why square integrable functions are, why the Fourier transform is particularly appropriate for square integrable functions. And the fact that the Fourier transform preserves inner products really means that in a certain sense the Fourier transform is a unitary transform. Because remember, unitary operators are such that if you have a unitary operator on some state psi and another state phi, that in the product is the same thing with the unit product of psi and phi. That's what characterizes the unitary. One of the things that characterizes the unitary. All right. Now, there's something even better about this, namely that the Fourier transform takes you from the space of square interval functions to the space of square interval functions in a one-to-one map. So it's a one-to-one map of the space of square interval functions onto itself, effectively, that's generated by the Fourier transform. And so that's a particularly nice mathematical theorem. And in particular, it's by square interval, one means technically the vague square interval. But I don't think we need to stress that. Okay, so far we've been talking about Fourier transforms, but it turns out that Fourier transforms can be differentiated in a very simple way. So, for example, f of x is the integral then of, say, f hat of k I kx dk over the square root of 2pi. Well, the first derivative then of x will just be d by dx. That x on the exponential brings down an ik. So this is minus infinity to plus infinity ik f hat of k d ikx dk over the square root of 2pi. And the second derivative then of x, f of x, is then minus ln k squared. So that is minus k squared f hat of k e3ikx dk over square root of 2pi. So differentiation is particularly easy if you have the function expressed in terms of its Fourier transform. The nth derivative by that I mean dn of f of x dx dn is integral minus infinity plus infinity ik dn power f hat of k dk square root of 2. All right, so is that, are there any questions about that? I guess I should not use the row as part of the blackboard. Okay, well, let's now talk about other. Really, if anybody has a question, it's useful. It's most useful to ask the questions during class, and then other students, older students, at least those present, get to hear what the answer is. Now, the next topic then is momentum and momentum space. So I'm going to use x is going to go to psi, so that we have this absurd convention of using psi for the wave function. Anyway, and we're going also to replace the wave number by p over h bar. This is This means that we get very ugly formulas. We get h bars all over the place. H bar, of course, is always constant over 2 pi. And we'll wind up sometimes with things in the form of 2 pi h bar, which is h written in stupid. But anyway, that's the way it is. All right. So psi of x equals, in terms of its Fourier transform, it's psi hat of k, that k is p over h bar, e to the I px over h bar, because k is p over h bar. And then we're going to have dk over the square root of 2 pi, but dk over the square root of 2 pi is equal to dp over the square root of 2 pi times h bar. And so what we're going to do is we're going to write this, we're going to put a square root of h bar here, and then dp over square root of 2 pi h bar, which of course, as I said, is just h. All right, so that's the kind of ugly formula we get, but this is what we're going to deal with. Now, this one, in this case, this psi hat of k is equal to the Fourier transform of psi of x. But what does the possible relation say? Well, it's going to say that. Let's first of all say that conventionally we'll normalize the function so that the integral of the square over all space is equal to 1. So we have 1 is equal to the integral from minus infinity to plus infinity psi of x absolutely squared dx. This is the probability psi of x squared dx is the probability that the particle is within dx over 2 of the point x. And it's got to be somewhere, so that adds up to 1. So this is then the integral minus infinity to plus infinity of the Fourier transform variable, and the Fourier transform variable, in other words, we can if we rewrite this, you see, we can say this is psi hat of k over the square root of h bar e to the I kx dk over the square root of 2 pi. Okay, with k p over h bar. So, the Fourier transform of psi of x is then psi tilde of k over h bar. And so we expect that this is dp psi tilde of p over h bar squared So let me just say this again. This is supposed to be the same thing as psi tilde of, let's see, psi tilde of k okay, so the Fourier transform is psi tilde of k over. See, there's a sort of inconsistency of this hat notation. Anyway, psi tilde of k over h bar is effectively. Maybe I'm using the wrong. Maybe I need to fine-tune this notation a little bit. So, psi tilde of. Well, let me just follow exactly what's in the notes. Okay, so this is integral f of x squared dx, which is integral dk minus infinity plus infinity of f hat of k squared. And now f hat of k is this psi hat of k over h bar. And so that's equal to this. So, but the notation is not good, and so I should have to work on that. In any event, what we normally say is, of course, that this is the inner product of the state vector and the position eigenstate x. And now I'm going to introduce something new here. Phi of p as psi hat of p over h bar divided by square root of h bar. And this is p psi. And the reason for that is that we want this thing to have a unit square integral, square integral. We want the integral of f by squared of this over all p to be unity. In that case, this relation here is 1 is equal to psi psi is equal to the integral dx psi of x absolute value squared. And this is equivalently minus infinity plus infinity dx psi x psi, and whereas this is the identity operator, and we can also write this as minus infinity plus infinity dp psi p psi, because the identity operator is equal either to the integral of x dx or the integral minus infinity plus infinity of p dp. Okay. And finally, this thing we want to say is integral dp of phi p, that's the value squared. All right, so in other words, the thing that's nice to deal with is not psi hat, but phi, defined as psi hat of p over h bar divided by h bar. And in that case, what we have is the psi of x is an integral minus infinity plus infinity dp over the square root of 2 pi h bar e to the I px over h bar phi of p, and the inverse relation is phi of p is equal to integral minus infinity plus infinity dx of the square root of 2 pi h bar e to the minus I px over h bar psi of x. Actually, I think I should have been calling this psi because I think it is. We're going to do psi of p. Okay, well, we can cast these expressions into Dirac notation by saying that this is equal to x psi, and that's equal to the integral minus infinity plus infinity x p dx dt. And whoops, this is psi. And we know what phi of p is, namely this. So by comparing these two expressions, we see that where we use this expression, P psi is psi of P. So this is the integral xp psi of P dP. On the other hand, if we compare this expression with that expression, then what we see is that xp has to equal to the IPX over h bar divided by the square root of 2 pi h bar. So by comparing these two, we arrive at that. This particular formula is used all the time in quantum mechanics, as you probably know. Questions? Now we have that delta function relation. One way of looking at it is to say that delta of x minus y is, of course, the inner product of x with y. And this we can write as the inner product minus infinity plus infinity x dp y dp. And now we have formulas for these things, namely that. And so we have minus infinity plus infinity dp e to the I p x minus y over h bar divided by 2 pi h bar. We're changing variables, just equals dk over 2 pi dvi k x minus y. Okay, we're sort of going around and around here. We saw over there that differentiation of a Fourier transform was particularly simple. Namely, you differentiate the function, just pull down an ik. So if you apply this over here, what we get is, I guess I'll go over here. What we get is h bar I dx with psi of x then, which we can write as xp psi, where p is the operator, momentum operator. This is equal to an integral minus infinity plus infinity dp prime x p p prime psi. And now p on the state p prime is equal to p prime on the state p prime. And so this is equal to an integral minus infinity plus infinity. I'll just write it in 2 different ways. p prime x p prime psi and xp prime, we know what that is. That's this phase factor that's so important. And so this is equal to integral minus infinity plus infinity dp prime over the square root of 2 pi h bar p prime psi of p dvi p prime x over h bar. So So that's the sense in which h bar over I d by dx can be used to represent momentum. In quantum mechanics. All right, another example. Questions? All right, another example is the uncertainty principle. And as I said, the uncertainty principle essentially there are many ways of thinking about the uncertainty principle. In fact, I bet everybody's a little bit tired at this point. I know I am. So let me, instead of going on and doing the next example of the uncertainty principle, let me give you an example of the utility of the uncertainty principle. Let's try to estimate the ground state energy of the hydrogen atom, just using the uncertainty principle. Okay. Well, what we have is the Hamiltonian is p squared over 2m minus p squared over r. And what we're going to say is that as we'll see when we discuss the uncertainty principle, the product of the uncertainty in G and the uncertainty in R is of the order of greater than or equal to h bar. Actually, h bar over 4 or something, but never mind. So we're going to say, now in fact, what characterizes the ground state? Well, it's the smallest possible value of p. In other words, you want to have as little momentum as possible because that contributes to the kinetic energy. On the other hand, you want r as big as possible. So you want small p, big R. On the other hand, what this thing tells us is that effectively PR, I'm just going to set it equal to h bar. That's how I'm going to apply the uncertainty principle. In other words, very crudely. So that means then that 1 over R, that P over h bar is equal to 1 over R, right? Okay. So this thing is p squared over 2m minus p squared p over h bar. Now we want to minimize that. So we set 0 equals the HDP, and that is p over m minus p squared over h bar. By the way, if I make a mistake, tell me, okay? We don't have much time left in this one. Okay. So that tells us that p is equal to m e squared over h bar, which has ringing something in my memory, so I expect it might be right. So what's the energy? In fact, I shouldn't have used h here. I should have used, let's just call that the energy. Estimate of the energy. So then the energy is going to be p squared, which is m e squared over h bar squared divided by 2m minus e squared over r, but that is minus e squared over h bar p, which is m e squared over h bar. Okay, so what do we get? We get in m e to the 4th over 2h bar squared in the first term, and here we have minus m e to the 4th over h bar squared. So the answer to the energy then is the energy is minus m e to the 4th over h bar squared.
To
To translate this into numbers, we can remember that the fine structure constant, I'm using here some sort of rationalized Gaussian units. I should have done it in pairs. It's easier to look at than rationalized. All right, anyway. E squared over h bar c is about 1 over 137. So in other words, E squared is equal to alpha h bar c. So this is minus m over 2h bar squared, alpha h bar c squared. The h bars cancel, and we have minus mc squared. Let me call you in about 10 minutes, okay, in class. So we have minus mc squared, the h bar squareds cancel, we have 1/2 alpha squared. Turns out, by luck, this is the exact answer. Well, for the ground state of hydrogen, Schrodinger's has given my simple Schrodinger's equation, ignoring spin, relativity, and everything else. So you see that this energy, the ground state energy, is minus mc squared. This is the rest energy of the electron, which is around 500 kilovolts, and then then a half, and then alpha squared. So in other words, it's minus 500,000 divided by 2 times 137 squared in electron volts. And anyway, this is minus 13.6. Actually, I've got a calculator in my pocket. Does anybody remember what the mass of the electron is? Is it 512? How much is it? 0.5?
So like
Huh?
511 kV or something like that?
All right. How the hell do you clear this thing? I'll probably every week. All right, let me not keep you here. It's 13.6. If I didn't make a mistake, that's why. Now, some of you, your homework is here, I know. Some people came in late. Who came in late? Okay. And so, this is yours, I think. And you work with a friend of yours. You want his?
Yeah, actually, this is my friend.
All right.
So,
Yeah. What is Monday? What is this rumor that Monday's a holiday? What is Monday?
I don't know. I know we have off.
We don't.
We know we don't.
We don't.
We have
We don't
Thursday. But not Monday.
Is it next week?
Yeah, not Monday.
Or Wednesday?
Well, we have Wednesday. Just Thursday, Friday.
So we have class Monday and Wednesday.
I'll break the Wednesday. All right, thanks.
Yeah, you're welcome.
Oh, this is my
Oh, yeah, okay.
There's a lot of so
I don't know. I guess a lot of kids have been studying.
that's there's one on
All right, why don't you go back?
or just someone just writing
Yeah, the scholarship stuff to get on my teacher's evaluation board.
You have a form.
I think it's online actually.
And I fill it out and give it to you.
I think I might just be able to submit it online.
All right, why don't you
That was
follow me to my office, because I'm not stupid. If you got something.